Today we're going to go over the thermodynamics test that is tomorrow. The first thing, which of the following are considered to be units of temperature or temperature scales? The first one, Fahrenheit, that's true. Newtons, that's not true. Celsius, that's true. Joules, not true. Kelvin, that's true. Kilograms, not true. For those that are temperature scales, how is the freezing point of water labeled? Well, for Fahrenheit, 32 degrees Fahrenheit. For Celsius, that's 0 degrees Celsius. And for Kelvin, 273 kelvins, no degree sun. Which direction does heat flow? It always flows from hot to cold. Which of these correctly show the direction of heat flow? 20 to 20, there's no heat flow there. From 20 to 30, that is not true as well. How about from 30 to 20? Yes, that is true. What about from 40 to 20? Yes, that's also true. From 30 to 40? No. And from 20 to 40? No. So only two of these are correct. If you apply 1,000 joules of heat to 10 grams of water, the temperature goes up 24 degrees. But if you put the same 1,000 joules into 10 grams of gold, the temperature goes up by 775 degrees. Why is this? Well, that answer comes to this equation. We can change the equation around to say that delta T is equal to Q over MC. What that means is that the change in temperature is proportional to 1 over C if the heat and the mass are the same. That means for a very small value of C, right here, temperature is large. And for a large value of C, the temperature change is small. Because water has a very high C, water is equal to 4.18 joules per gram degree Celsius. It means it takes a lot of heat to raise temperature just a little bit. But gold, on the other hand, Au, its heat capacity or specific heat capacity is 0.129 joules per gram degree Celsius. That means it's almost 30 times lower specific heat or specific heat capacity, which means that the temperature change for the same amount of heat is going to be 30 times more. So low specific heat means high temperature change. Two beakers of water at different temperatures are mixed. What is always true about these beakers? So let's suppose I have one beaker that has 20 degrees C water in it, and I have another beaker that has 30 degree C water in it. What can I say about the temperature? Well, what I know about the temperature is that it's always going to be somewhere in between here. It will be closer to the one that has the larger mass. If they both have the same mass, the temperature will be exactly in the middle. But it can never be below the lowest temperature or above the highest temperature. It's always in the middle somewhere. When you break something, what happens to the entropy? Well, first of all, entropy is disorder. Make sure that you know that it's disorder and not order. So what happens to the entropy of the object that I break? Well, its disorder goes up. The entropy of the universe as a whole also goes up. So the universe is more disordered, more chaotic, because I broke something. Now when I organize something, like sort my homework papers alphabetically, or build a log cabin out of toothpicks, or create a tree by photosynthesis out of random carbon dioxide molecules in water, what happens to the entropy? Well, the entropy goes down because I've made something. I have made it more ordered, so the entropy, the disorder, goes down. In order to do this, which doesn't occur naturally, I have to do work. So I must put energy into the system and do work on the system in order to make it more organized. The universe as a whole, however, goes up. You'll notice that the entropy of the universe always goes up. No exceptions, ever. So if you think the entropy of the universe is going down, that's a wrong answer. How about these various situations? How is heat transferred? We're talking about conduction, which I'll label Cn, convection, which I'll label Cv, and radiation, which I'll label R. Heat arrives on Earth from the sun. That's radiation. And it is the only type of heat transfer that can occur in a vacuum. There is no need for any medium to transmit the heat. If I burn my hand on a hot piece of metal, that is conduction. Hot air from a space heater rises, so that's convection. If I hold my hands beside a fire and feel the warmth, that is radiation. Over here, a burger cooking on a frying pan. Here's my frying pan, and here's my burger. It's in direct contact, so the heat flows straight into the burger, so this is conduction. And if I'm heating water in a pot, then what's going on with the water? The water is convecting. It's circulating around and carrying the heat physically from the bottom of the pot to the top. So this one is Cv, convection. So define heat. Heat is the energy transferred between objects. So it has units of energy, which are joules, but it's the transfer of energy from one object to another, or within an object from one end of it to another. In the example of, for instance, heating up one end of a metal rod or a spoon, the other end eventually gets hot. It occurs because there is a temperature difference between the objects or within the object from one side to another. An object does not have heat. It can have internal energy, but there's no such thing as something having heat. Heat is the flow of energy. It is energy in motion. So what is temperature? Temperature is a measure of the average kinetic energy of the atoms or molecules in a substance. These words are important. It differentiates temperature from internal energy. Internal energy is the total amount, I'll write the word total in here, of energy in an object due to the internal motion, which is kinetic energy, just like in the previous definition for temperature, and also potential energy and other things associated with an object or a material. But we cannot measure this directly. So I'll say CANT. We can't measure internal energy directly, although we can see if it goes up or down because we can put heat in or get heat out of an object, so we can see how much it changes, but we can't measure it directly. These two definitions are very similar. Both involve kinetic energy, so they're very often confused. But temperature is a measure of the average kinetic energy. Internal energy is a total energy in the substance, and we cannot measure it directly like we can temperature. They're very similar definitions, so you have to be very careful when you're looking at them. Specific heat capacity. What is it? The specific heat capacity, or C, is the amount of heat energy that is required to raise the temperature of, in our case, 1 gram of a substance by 1 degree Celsius. Now there are other units. We could use kilograms or kilojoules. We could also use calories. We could use degrees Fahrenheit if we wanted to. But for us, we say it's the amount of heat energy in joules that's required to raise 1 gram by 1 degree Celsius. The specific heat capacity varies by substance. So, for instance, water has a specific heat capacity of 4.18 joules for every gram and every degree Celsius that it changes. Whereas gold, AU, for those of you who took chemistry last year, has a specific heat capacity of 0.129 joules per gram degree Celsius. Its specific heat capacity is much lower, which means that a small amount of heat will raise the temperature of gold quite a bit, but the same amount of heat will barely raise the temperature of the water at all. Water has the highest specific heat capacity of any normal substance that we find in nature, which means that water's temperature changes only very slowly and requires a great deal of heat input or heat output in order to raise it or lower it. What's the difference between an insulator and a conductor? An insulator is something that does not allow heat to go through it very easily. Examples of insulators are air, wood, things that don't have free electrons like nonmetals. That's an M. A conductor is something that does allow heat to transfer very easily, and some examples, or a very good example of a conductor of heat, is metal. Insulators and conductors of heat are often insulators and conductors of electricity as well. Suppose that you feel the wood on your desk, and you also feel the metal chair leg. The metal chair leg feels colder, even though they're both sitting in the same room. They've been sitting there all day long, so they must be at the same temperature. Why does the metal chair leg feel colder? Well, the truth is that you can't feel temperature. You can only feel heat gain or heat loss. A lot of people don't realize this, but you can't tell the temperature of something by feeling it. You can only tell if heat flows in or heat flows out. When you touch the wood on your desk, the heat begins to flow into the wood and then stops, because wood is a good insulator. And you can't feel any heat loss because no heat is going into the wood just a brief time after you touch it. A metal chair leg, however, feels colder, and it feels colder because it's a good conductor. As soon as you touch the metal chair leg, the heat begins to leave your body and go into the chair leg, and you can feel that. It continues to go because the heat is carried away because it's a good conductor, and you continue to feel the heat loss, therefore it feels colder. But in reality, both the wood on the desk and the metal chair leg are exactly the same temperature because they have been sitting in the room and have reached thermal equilibrium in the room, so they're the same. All right, a little confused here, messy looking slide, but zero. What does zero mean in the various scales? Well, first of all, 0 Celsius is the freezing point of water. So the freezing point of water is represented by 0 Celsius. 0 Fahrenheit, which you're not going to be tested on, is just what some old dude thought was the coldest you could get. And he had put salt on ice, and that was as cold as he could make things, and he decided to call that 0. Kelvin temperature is an absolute scale. These other two are relative. But Kelvin is an absolute scale. 0 Kelvin has another name, and we call that absolute zero. And that is the temperature at which all atomic and molecular motion stops. There is nothing colder than 0 degrees Kelvin because you can't move any slower than being completely stopped. And remember that temperature is a measure of the average kinetic energy. Kinetic energy is the energy of motion. And if you're not moving, then you've got no kinetic energy. So 0 Kelvin is the lowest you can go, and there's no such thing as a negative number in Kelvin temperature. If you mix 3 liters of water at 20 degrees and 3 liters of water at 60 degrees, you end up with 6 liters of water at what temperature? Well, this one is an easy one because we have the same mass of water at each temperature, which means that the temperature will be exactly between the two. And right exactly between 20 and 60 is 40 degrees. We can prove it. 3 liters of water times 20 degrees plus 3 liters of water times 60 degrees is equal to 6 liters of water times some temperature, final temperature. When we solve this, we get 60 plus 180 is equal to 6T. 240 is equal to 6T. T is equal to 240 divided by 6, which is 40 degrees Celsius. This right here, this equation, is just the weighted average of the two liquids. If one of these liquids was, for instance, a different number, say 4 liters, that would make this 7, and we would have to do the calculations again, and we would come out with a number that was closer to the larger number. It would be closer to 60 than it was to 20 because there was more mass. Now this equation does away with the value of C for water, which is 4.18, that's a 1 in there, joules per gram degree Celsius, because both substances are water. When we do the Qn, the heat in is equal to the minus of the heat out. What ends up happening is that the C on both sides of the equation disappears. They cancel each other out, and that's why we don't have to use C. If the two substances were different substances, then we would have to go through the whole thing with the specific heat capacity and C for each side of the equation, just like we did in the lab with the metal going into the water. So when we have heat gain or heat loss, how can we calculate it? Well, we're going to use the equation Q is equal to mc delta T, and we're just going to substitute in our numbers. Q is equal to 75 grams times 4.18 joules per gram degree Celsius times our temperature change. Well, 90 degrees cooling to 20 degrees is a minus 70 degree Celsius temperature change. We look at the units, grams cancel with grams, and degrees Celsius cancel with degrees Celsius. So we end up with a final number when we do the multiplication of minus 21,945, and the only units we got left are joules, so that's joules, and that's the heat loss when we cool the water down. That's how much heat it has to give up to change its temperature that much. Okay, in this case, what we're going to do is we're going to take the equation Q is equal to mc delta T, and we're going to solve for delta T. And to do that, I have to divide both sides by mc. We end up with delta T is equal to Q divided by mc. So it's going to be equal to the 3,500 joules divided by 1,500 grams of iron, and also divided by the specific heat capacity of iron, which is 0.45 joules per gram degree Celsius. And I can do this math, and I get about 5.18 or 5.2 degrees Celsius. So all we did was we took Q equals mc delta T and solved it for delta T. Alright, this is the most complicated equation you're likely to see on the test. This is just like the lab. We've taken a sample of metal and put it into water. It raised the temperature of the water by a certain amount. And we want to find out what is the specific heat of the metal. So we're going to solve for C. But to do that, first thing we need to do is figure out the heat gained by the water. We can do that with Q equals mc, let's see there, delta T. And so we can substitute the Q for the water is equal to M for the water, and the mass of water is 1,800 grams, times C for the water, which is 4.18 joules per gram degree Celsius, times the change in temperature of the water. Well, let's take a look at the change in temperature for the water. It went from 25 to 29.8, so that's 4.8 degrees Celsius. When we do that, we get a value of Q of 36,115 joules. Well, now we need to solve for this heat. Obviously, the Q for the water, it's a W, is equal to the minus Q for the metal, because the heat that went into the water all came from the metal. We need to solve for C for the metal, and C is equal to Q divided by M delta T. We're using the same equation that we used before, this one up here, Q equals MC delta T, and solving it for C. We substitute our numbers, and I'm going to put in my negative 36,115 joules divided by the mass of metal was 620 grams. And the delta T is what? Well, 95 degrees is what it started at, and it ended at 29.8. So it cooled off. So the temperature is 65.2 degrees Celsius, and it went down by 65.2 degrees Celsius. Now, if you notice, there's a minus sign up here and a minus sign down here. They're going to cancel each other out, and I'm going to end up with a positive number. I should always end up with a positive number when I solve for C, the specific heat capacity, or if I solve for M, because there's no such thing as negative mass. When I do this, I end up with 0.893 actually joules per gram degree Celsius. This number is very close. 0.899 is aluminum. So if I was trying to figure out what my unknown metal sample was, and I had a list of the value of C for various metals, I would see that this is most likely aluminum, because we're very close to that value. In this case, we're going to solve for the mass of zinc. It says a piece of zinc with a C of 0.388 joules per gram degree Celsius requires 3,000 joules of energy to change from 50 to 70 degrees. That's a 20 degree temperature rise. And they ask us, what is the mass of the zinc? In order to do this, we're going to solve Q equals MC delta T for the mass. We have to divide it by C delta T on both sides. And when we do that, the C's cancel and the delta T's cancel. We end up with Q is equal to what are we solving for? We're solving for mass is equal to Q divided by C delta T. So we can do our substitution. I'm going to move down here. M is equal to, well, 3,000 joules, they gave it to us, divided by C, they gave it to us as well, 0.388, and that's joules per gram degree Celsius. And our delta T, we said, was a 20 degree temperature change, 20 degrees C. None of the units cancel. You'll notice joules up here, these cancel, and these joules cancel, and this degree C cancels, and this degree C cancels. So cancel, 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 cancel. It leaves us with 1 over 1 over grams. The answer is in grams. M equals, and that's something like 515 grams of zinc. Okay. Last slide here. Each of the following materials are given the same amount of heat energy, which is 2,000 joules. It doesn't really matter. They all have the same mass. So basically Q and M are the same for every sample. Which of the material is going to gain the most temperature? Well, the use of that word most, if you're looking at test taking strategy, tells us, since we have a big list of numbers, that one of these, either the biggest number or the littlest number, is going to be the correct answer. And we already talked about this, but the change in temperature is proportional to 1 over C if Q and M are constant, which means a very big C is going to end up with a very small delta T, and a very small C is going to end up with a very big delta T. So the lowest specific heat has the highest temperature change, and what that means is that lead is going to have the highest temperature change. If you can't remember that, think back to the lab and remember that when you put the metal in the water, the metal went from 100 degrees down to about 23 degrees, which meant that it had a 77 degree temperature change, minus 77 degrees Celsius. That was the metal temperature change in the lab. The water, on the other hand, went up from maybe 21 to 23 degrees, which meant that it had about a 2 degrees Celsius temperature change. So the change for the metal in the lab was very high, and the change for the water in the lab was very low. If you can remember this, you ought to be able to answer this question without any problem at all. The metal is always going to have a higher temperature change than the water, given the same mass and the same heat put into or taken out of the sample. So the lower the value for C, the higher the temperature change. And that's it. Good luck on the test.